And I am delighted to introduce our second speaker, Professor Raffaele Pisano from University of Lille, who is going to talk about the symmetries in the history of physics, phenomena and ideas in Maxwell, Noether, and Einstein. So, join me please to welcome Professor Pisano.
So good morning. Thank you very much for the invitation and for organization. So thank you for the previous colleague that talked about history of science, history of physics, so I go faster through some things. I will focus on Maxwell, Noether, and Einstein symmetry. Perfectly, I would like to talk about the mechanism ideas that produce a symmetry in physics, because I think it's more interesting to understand how some reasoning arrived to talk about symmetry, because we know the symmetry, conservation of law, etc. But into the history of science, particularly in the history of physics, it will be interesting to understand the intellectual part of the science, the reasoning that we have in background. And sometimes it's not so complicated, it's complex, and sometimes, very often I have to say, it is fascinating because it's come out from things that maybe are not so strictly scientific, like we know, like we use the term scientific today. First, I would like to precise that I'm a historian of physics and physics mathematics and busy with the relationship between physics and mathematics. I mean, I investigate mathematical objects and physical objects in an ancient theory, in the history of science, and try to understand how they are connected from intellectual point of view, and after from mathematical and physical point of view. The result in physics and mathematics is interesting, but how to connect two quantities, just an example, Leonardo da Vinci, he understood that if I have the cannon in a certain position with a certain degree, I have a different range on axis X. He understood, but he was not a great mathematician like Pacioli, for example. He was a genius, but he understood with a picture, just with a picture. He tried this, like we know nowadays, but it was not formalized. Then, Sadi Carnot, in Réflexions sur la poisson motrice de feu, 1824, the founder of thermodynamics with the second principle of thermodynamics without the first one, so we have an historical inversion. He proposed this cycle with the geometry, with the cylinders. Clapeyron later, 1834, proposed the same cycle from an analytical point of view, because he said, my friend, after that, from Polytechnic school, it was not so well understood. So I wanted to reformulate from an analytical point of view. Nowadays we study this. It's a Clapeyron cycle. This is not a Sadi-Carnot cycle. But we used to say Sadi-Carnot cycle. The difference is, and my interest is, where are physical and mathematical objects and how they are linked into the history of physics? Here. This is the real result. Or this is just in background. And in fact, we have this. The result. This is only another way to express from an analytical point of view. So we have different kinds of mathematics, a different physical approach into the history of physics. This is my line of research. So what is the story? I will try to introduce the mechanism, an intellectual mechanism to idea to arrive to talk about symmetry. Of course, we cannot talk about symmetry in the past. The concept of symmetry is a modern term because we constructed an idea from mathematical, formal point of view. But in the past, we had ideas that are right to talk about what we use today to call symmetry, but this is not really the same concept that we used to do today. I will try to focus on Maxwell, because I told you in the background, the ideas, the phenomena, etc., because Maxwell was one of the first, we cannot say in the history of science who was the first, but he was one of the first to use a mathematical formulation from another theory in a new theory, electromagnetic field. I mean, I'm talking about LaGrange formulation. But he did not use immediately. He tried to understand and explain pedagogical point of view too in his book, what is the method used by LaGrange and what am I going to use part of his formulation. And we will talk about the symmetry in what we used to call symmetry in Maxwell equations, etc., etc. I will focus on Noether, because Noether used the Lagrange formulation to try to talk, to enlarge in modern terms the concept of the symmetry and exactly the conservation, the relation between physics and mathematics, geometrical physical mathematics, when she arrived to talk about the conservation of certain quantity and symmetry, etc. We will see that Maxwell never used the concept of mass. Maybe he was one of the first theory into the history of science after thermodynamics, after analytical theory by Fourier, etc. We have new quantities for a new theory. It was not easy. Now we used to study history, to study science, and we don't take care if we have a mass. This concept of mass does not exist anymore. And just a little bit in intermezzo, and I will focus on Einstein. On Einstein, I will just focus on some particular aspect because we know the invariance of C and the first principle, etc. So we try to understand what is the background. Generally speaking, what we can arrive to talk about symmetry because we have an intellectual mechanism before and after formal mechanism that are right to talk about this. As I told you in the past was not so. So some particular concept that we used to call symmetrical today are nothing to do with symmetry and nothing to do in the past with the concept of symmetries, because symmetrical maybe cannot be the same symmetries what we used to say today. If we talk about Aristotle, we talk about science of weights by Tartaglia, etc. We used to call a lever with two masses. He tried to understand when the masses are in equilibrium, and this is not symmetry. But how can I arrive to have an equal mass in this lever? How can I arrive in equilibrium that is different from to have equal masses on the right and the left? So I have to change something. This reasoning to change something is in effect the tentative to arrive at sort of invariance of the problem, generally speaking. So we have harmony, equality, regular relationship, invariance, etc. Of course, we arrive today, we talk about parity, etc., and other kind of symmetry. They have a formal aspect of the science. So in the past, my colleagues before talked about this. The mechanism was the proportion, to arrive to put something in proportions and to create an harmony. The concept of harmony is very interesting because some scientists use it in different way. Sometimes ontological, but sometimes very metaphysical, like a Kepler, for example. And sometimes, because we talk about the concept of the sphere, Aristotelical perfect object, and if we talk about the Coulomb, la balance de torsion de Coulomb, and if we talk about Volta battery, we can arrive in some way from epistemological point of view to this, because it was done a research with Charles Gillespie in the past, and me, and we arrived to conclude that maybe when Alessandro Volta was on the court of Napoleon, he met Lazare Carnot, the father of Sadi Carnot, and he proposed to him this general view of a machine en general to study the efficiency of a machine. So just to say that how we can consider something harmonical different from symmetry, how we use today. So Maxwell, that is in depth completely, he wrote in his preface with the Faraday, produced this new theory. I told you without any kind of concept of mass, it's very important because we arrive with the paradigm, Newton paradigm arrived, Newton paradigm by Newton science. Newton paradigm arrived until the end of the 19th century with some concept like impossibility of a perpetual motion, etc., etc. The first law of inertia was a debate until the end of the 19th century, etc. And this, all of a sudden, happened by a genius, because he was really a new genius. He built this new theory, put together physical and mathematical object of two theories, electrical and magnetic. And he produced electromagnetic field. But he had no possibility to take into account Newtonian science, Newtonian equations of motion, and he used the Lagrangian one, of course, because for evidence that it's to everybody. First of all, there is a little bit of confusion about Maxwell equation, not because we know that someone else put together this Ford equation, etc., because the conception of these sets of six of those 8 equations with the 3 separate equations, about 20 variables, etc., was part of a book of a publication, 1865. But most refer to this abstract. They have the same date, the same name. In effect, in this abstract, he wrote never about equations. We don't know what he did in the conference that when he read this. But if we have to speak strictly to the history of science, we have this abstract with the same title of this, but in this abstract, 1 year before, we have no information about the equations. This is important because we have to take in consideration that this document as the start of the equation. Like we know nowadays, these in modern terms, you can write in different terms too, if you will, with other aspects, depend on what you want to do on this. What is interesting that Maxwell adding the displacement current to Ampere law, and he arrived later, posthumous, described to electric field and magnetic field. It was intuitively because we can take in consideration some quantity of a theory, another quantity of a theory, put together the idea, and we say they are symmetrical. How can use, in mechanics I have mass, in electromagnetic field I have the charge, etc., etc. But is an intuitive way to arrive to talk about symmetry from this point of view. First of all, the first Gauss and the third Ampere relationship, electric field and source, magnetic field and the source, moving charge. The first and second, 2 fields, 2 flows. In this sense, we can use to talk about symmetrical point of view between 2 fields, 2 theories. The third, Faraday Maxwell and the Ampere Maxwell, 2 circulation, 2 fields. But parity, like we used to call today, lacking. We have an absence of magnetic point charge source because we have a moving charge, so the charge in movement produces current electric. The first and the second, since the magnetic field always have 2 opposite poles, then the magnetic field equation reduce. This is why we have, for example, different type of field lines and the different result of flux of 2 lines. The third and the fourth to a magnetic induction field generated by variation of magnetic field does not correspond in the fourth similar terms. In other words, the following hypothetical law, a variation of electric field generated in magnetic induction fields, we cannot claim. the third and the fourth, both magnetic and electric fields appear, one can infer that they are two separated phenomena of a unique theory. And the electric field and magnetic are specific cases of electromagnetic field, no moving charge, etc. So we have this idea of, when we talk about Maxwell equation, we can use this symmetrical idea of a concept, but if we go in details, they are not so symmetrical. If we want to take in account the LaGrange formulation in Maxwell, to move from mechanics that studies some particular objects, okay, and in other theory, we are talking about a theory completely different. If we take, just one should think that when we talk about mechanics, we can have possibility to see objects in movements, not at the level of physical mathematical mechanics. But when we talk about the electromagnetic field, like thermodynamics, we talk about something that we cannot see. This is very important for who invented the theory. It means that the mathematical formalism should grow up if I want to explain and justify some result. So Maxwell expressed motion and energy relation within the system, and before he said the aim of LaGrange. Now there's a lot of writing about Maxwell about LaGrange. He didn't want to say to the reader, this is the LaGrange formulation that applied to arrive at. He tried to explore with the reader how can use this formulation in another theory. This was a challenge for him, because the reader that he used to read Lagrange formulation or Lagrange equation in mechanics, now they have to talk about electric charge and other things completely different. So the aim of Lagrange was to bring dynamics under power of the calculus, etc. And he said, I have applied this method so to avoid the explicit consideration of the motion of any part of the system, expect the coordinates of variables. And he said, there is a third method of expressing the kinetic energy. I want to explain that he could not use Newtonian science for many reasons, but also because Newton had not the concept of energy, because no concept of friction, etc. With the Lagrange equation, we have the concept of energy, etc., because we have the concept of friction, and because we have the concept of the idea of the force and displacement, okay, and the integral, the work, etc. There is a third method of expressing the kinetic, which is generally indeed regarded as a fundamental one. And he used this third method. He proposed to the reader three methods, and the third method was the Lagrangian one. So I do not, this is how he arrived to talk about the motion of electricity, the motion of system. The motion, that if we talk about motion in electricity, we have to think about the charge in motion, so the concept of electricity. But the real concept of motion in mechanics is very important, and it is completely transported to in another theory. This is mechanism, is intellectual mechanism, is what is a challenge for who, like Maxwell, wanted to create a new theory. So Maxwell put in mathematical language the experimental result obtained by Michael Faraday. This is who he said at the beginning in the preface, etc., and described his experimental research in electricity. But he first discussed it and only then used the Lagrange method for a connected system. So the interplay is the main physics mathematics apparatus Lagrange formulation. Please pay attention that I wrote physics mathematics, not physical mathematics, not mathematical physics, and not physics tier mathematics. Because it's a part of history of science, just after Fourier and before Maxwell, that we have a very particular point of view, particular approach to build a new theory, where the concepts were not physics, not mathematics, but at the same time, the objects were physical and mathematics. So we read in some books, physics, mathematics, not mathematical physics or physical mathematics. I have no time to go into this, but we can talk about later. Noether produced, one can say with Noether we have for sure the first idea of symmetry in physics, produced with the two theorems, you know very well, so I do not focus on the sentences, etc. But after that of Maxwell, a new relation between mathematics and physics was born. Symmetry from mathematical point of view and conservative laws from physics is very, very interesting from, like I told you before, what are the physical and mathematical objects in a theory and how they are linked. This is the paper, and this is translation. Of course, she was involved in a very interesting discussion, very important. It was helped, we can say helped, or we can say she was in a very good environment, we can say, from intellectual point of view. Excellent environment. What is interesting in this paper about the relationship between the physics and mathematics is that she put together algebraic topics, differential invariant studies, Riemann geometry, calculus variation, LaGrange mechanics, field theory, group theory. So we can open a book for different level of master, different books. She wrote everything in one paper, the result and the mechanisms to talk about symmetries. Result may deal with an invariance, the action integral in mechanics, physical system, otherwise Lagrangian. The operation developed under transformation, continuous and discrete, etc. The property relation of a symmetry are explained by its effects themselves realized. So this is a simplification how she arrived to talk about the Lagrangian in physics, but I want to focus you on that. The idea, the mechanism, intellectual idea was, I have something, I arrive to the result, and I find not the result with something else. So what is, from mathematical point of view, we know very well what is epsilon, etc. But if we go back in intellectual history of science, we can see that from epistemological point of view too, because it's an interpretation, if you like, we try to give an interpretation of this idea. I'm not saying that she used this idea. This is an epistemological interpretation based on the facts, so historic epistemology of science. In the end of 18th century, Lazare Carnot, the father of Sadi Carnot, wrote papers, books, and the two memoirs for a prize proposed by Académie des Sciences. He lost, and the Coulomb, Augustin Coulomb, won it. It was on machine, on mechanical machine. They tried to find the efficiency of a machine. He produced his mathematics in alternative to Newton 1 and mechanics. He arrived to a first multi-body system law, and is a conservation of angular moment and the conservation, etc. So he arrived he proposes something that was not included in Newton's science, the concept of conservation, etc., etc. This is chronological to understand. What is interesting is that to arrive to produce these vectorial equations, he used for sure an ancient method, synthetic method, that go back to the Pappus. The idea was, I have a physical system, I add a quantity, I do an operation, I do something, I have an idea, and I say, from this idea, I can add something. After I found a physical mathematical solution that include what I already added. So if I want to go back to physical thing, what I have to do? I have to delete this initial idea. This simple intellectual idea to produce a result include, because the ancient times, this circular idea that he called mouvement géométrique, geometrical motions. The son of Lazare Carnot wrote Réflexions sur la poisson à motif de feu in 1824, the only one book that he wrote. And the father passed this idea of a circular, of a cycle, etc., to Lazare Carnot that produced his second principle of thermodynamics without any kind of mathematics, only one footnote, a little bit wrongly, from page 73 to 79. What happened at the beginning of the next century? So how we can arrive to talk about the real symmetry, what we use today to call symmetry? We have to pass for this crisis. These crises, like all crises, are not so negatives. Sometimes can be positive. We can take the positive things from the negative. But in this case, we have the changes. So the main problems was that the physics can have a non-Euclidean geometry too. It was a shock because all physics until the end of the 19th century was based as a sister in Euclidean geometry on the postulates, axiom, etc. And now two people said, no, this is not. It's possible to find something coherent, logic, and we can use it. And with the birth of thermodynamics that have nothing to do with the Newton paradigm, with the birth of electromagnetics that have nothing to do with the mechanics, only because we used LaGrange, etc., but not with the Newton mechanics, they need to discover, to talk, to work on new quantities, new ideas. I mean, black body radiation theory, the Einstein ad hoc hypothesis to help Planck to resolve this black body radiation theory, etc., etc., etc. So we have in this period non-Euclidean geometry, black body radiation, definition of initial time for a given stationary system, measure of length for magnitude in motion, compatibility between two main principles of relativity, covariance of a physical law in Lorentz transformation, hypothesis for internal natural bodies, etc., etc. And the space can be non-Newtonian one. This was another shock because Einstein talked about his principle, said not because said what Newton did is not good. Thanks to what Newton did, we can go over. We can continue to talk about something else. What about the motion at velocity of light? To the position we should add times measuring space and using the property of simultaneity. Here we start to have the concept of invariance that are very important. I don't go into that from Galileo to Lorentz, etc. Everybody knows this. But I want to show you this ad hoc chronology that I propose to you to try to see, because sometimes in history of physics, history of science, it's nice to see a chronology to understand the ideas of a genius like Einstein, how they worked in the years. There's a period he worked with the three articles, very interesting. He continues in 14 with the formal foundation of general theory of relativity on the relativity problem, etc. And after on the influence of gravitation of propagation of lights, the speed of lights and statistical gravitational field, etc. Until 27, we can say, more or less, of course. We don't know really what he did in the middle and after, if it's necessary just a talk with another scientist to understand something more. So we don't know. This is the fascinating thing of history. But taking account, if we go back to 17th century, based on Euclidean geometry, for speed inferior to the speed of light, we can talk about its homogeneity, its isotropy, uniform time, etc., etc. But if we take into account this kind of motions in this kind of frames, this kind of objects, this kind of physics, what about if we move at the speed of light? And if we talk about a kind of symmetrical point of view here, we have the same symmetrical point of view here if we talk about, if we move at c, speed of light, and fruit of a new physical mathematical relationship, space-time symmetry, time independent, different from dynamical symmetry, not stationary time dependent. So Maxwell claimed that in vacuum electromagnetic waves propagate at the same velocity, same. It's intrinsic invariance, we can say. Galilean relativity we know, and this transformation for inertial frame system. It's very interesting the use, put in the intermezzo, the Michelson-Morley experiment, and we arrived to famous principle. The law of physics are the same in all inertial frames of references. The velocity of light in the free space has the same value, say, in all inertial frames of references. If we take into account Lorentz transformation, we can, from Lorentz point of view, not from Einstein point of view, but we can have the concept of simultaneity, dilatation, length, contraction, etc. But this is another approach. It's really from mathematical point of view, because we focus on the term 1 on gamma. So, the first concluding remark, the symmetry, application of symmetry of the mathematical equation with respect to certain parameters. In other words, the symmetry described by certain group of transformation which produce an invariance of this equation. I mean that if we want to talk about symmetry, now in the terms nowadays, we have to talk about 1, the reasoning in background, 2, the kind of and the use of mathematical apparatus that we want to use to talk about symmetry. Because I can talk about proportions, or I can talk about something complex like a Noether date. It's interesting to understand that, than more to understand the results of a symmetry. Symmetry application in modern physics, invariance principle or principle of symmetry, physical laws are invariant in every inertial frames, etc. This is the result of a reasoning. Certain theories are based on symmetry properties, the group of transformation, etc. If we read Noether and we read Maxwell and we read what he did Einstein, we find the same. We can arrive to talk about the symmetry in some way, but they use different approaches. This is not banal. We can say yes, why not? But different approaches in different fields. So, about Maxwell, a new physical theory with a new mathematical framework, a new relationship in physics between physics and mathematics with respect to Newtonian paradigm science, LaGrange method and LaGrange formulation. Noether, based on Maxwell-LaGrange framework, a new relationship in mathematics between mathematics and physics, symmetry, mathematics, and conservation law in physics. I say general way, okay, we can go into details. Einstein, symmetries, a relativity, new physical principle to explain new phenomena mechanism on physical and velocity is a C. If we see this relativity in this way, we can read Einstein in a realistic way. A new relationship in physics between mathematics and physics, invariance in mathematics of a law on physics. So, what we do nowadays, taking account the history we said, what is interesting is the breaking of a symmetry. What is interesting is how we have this situation, and hidden symmetry, of course, because it can explain something more that we can have to discover now or later on. By the way, the symmetry, general speaking point of view, from the ancient time to the modern time, resume a relationship between a way to see the nature, natural phenomena, physical, nowadays physics, or philosophia naturalis, if you want, and mathematics, where the mathematics can be geometry too. If we talk about Kepler or we talk about Gibbs, the use of geometry to talk about entropy, etc. I let you with this. We used to do in the summer school in Lille for master, a PhD student, and early career professor. We did not in 2021-22 because of the COVID. We tried to do in 2023. We have people all around the world, from Agassi, Krog, etc. We have lots of PhD students. Mozzarella from Napoli, where I come from. Directly from my father, in 2 days arrive and fresh. I promise, every time. And so what I said you can find in my last books. The last was this. And the new one is this, just arrived from Springer, but it will be published 2023. This is in preprint, but I'm completing. Thank you very much, and I hope that explained.
Questions? Yes, here. Yeah.
Einstein over the years made many attempts to unify
the one before.
electromagnetism and general relativity, including very complicated mathematical constructions. In doing so, was he ever led to introducing new symmetries?
From an electromagnetic point of view?
Any beyond those already known about of general relativity, the requirements of covariance, charge conservation, and so on?
Yes, you are right. He wrote. In his writings, we can read several ideas, produce several arguments on. If we talk about the Nobel Prize in 2021, he was on the photoelectric effect, etc. So he was very in the matter. But from a symmetrical point of view, I proposed this to the concept of invariance because I wanted to be linked from exposition, to be linked with the concept of symmetry in Noether, that it was connected with the Lagrangian. This is the choice that I did in my presentation, but you are completely right that in previous we cannot say writings, we can say, because in Einstein we find, when we read maybe a paper, it's very interesting because we find some ideas that go back another paper and we can say, he said, he used it, he found it. But I wanted to use the idea, I wanted to propose, to show the result of how can I arrive to the two principles of invariance of C and the idea that the physical principles are the same, for all observers. But you're right.
It's interesting that Weyl, when he attempted to unify theory, came up with the whole idea of gauge invariance, which now is central to everything in physics.
Thank you.
To talk about the symmetry, whole history of symmetry, like our colleague did before, we need more time because the concept is not always the same. It changed from the cycle, from the symmetrical, no symmetrical, but nowadays we are lucky because we talk about symmetry from mathematical point of view. We use mathematics to understand the symmetry. So we are lucky because we cannot produce error in ideas in background.
Before we get a question, may I ask you please to have the slide before this one? Someone from the room asked.
Just before?
Yes. No. this one. Yeah,
Okay.
could you please? Yeah, thank you.
To continue the discussion on Einstein, I think you mentioned in one of your last slides also the emergence of gauge theory,
Yeah.
and gauge symmetries, and I think this is another interesting example to underline the difference between a mathematical approach and a physical approach.
Exactly.
Because in 1918, you will know that, of course, there was a famous discussion between Einstein and Hermann Weyl, because Hermann Weyl came up as a mathematician with the ideas of gauge theory, which he found as a mathematician in the context of differential geometry. But the consequence was that the length of the measures is changed by these gauge transformations, and then Einstein, that was a physicist, like Newton and Leibniz, which I mentioned before, and he said, a wonderful idea, but it is false in physical context. And then he came up with these well-known examples, but nevertheless, this mathematical idea, we will hear about that more on this day, during this day, would become very influential in quantum physics and elsewhere. But I think it underlines again the difference of mathematical fascination of symmetry, gauge theory, and on the other hand, the physical instinct of Einstein.
Thank you.
Of course, I agree with you.
First and then, yeah.
Yeah, thanks so much for this great number of historical examples. I'm just wondering, what about, say, the older quantum theory, so Planck's contribution? So there was Kirchhoff's law of radiation, and there was lots of discussion. So Kirchhoff first tried to prove it as a physicist, saying if you have a black body cavity and this could be made of different material, there should be a unique formula for black body radiation. And then later Planck in his book proved it just by a geometrical argument. Later in 1912 Hilbert said, well, there's a flaw in Planck's proof, I'll do it with integral equations. And then later Pringsheim told, well, you have to recur somehow to physics in order to get this unique formula, for which Planck then had to invent the quantum theory, the quantum hypothesis. So I was just wondering, is this a story of symmetry, or is it an interplay of physicists arguing there should be a general formula independent of material properties, and therefore it's unique and we have to resort to some logical mathematical arguments in order to fix it? Or is it a physicist's kind of reasoning, since there must be some kind of equilibrium, or if there would be a body which absorbs one wavelength and emits another one, then you have a perpetuum mobile or something like this. So I don't know whether you came across of this example. I just wonder whether it fits in these more, say, geometrical examples we have at this time.
Thank you for the reflections, for the questions. It's very interesting. For sure, there is a part of geometrical ideas that you said, for sure. I don't want to say at first glance that really it is a part of the... If I study history of symmetry, generally speaking, or if I try to write a paper on history of symmetry, I put in footnote black body radiation, because it's not so important, because there are other many things that we have to say about this. But black body radiation, it was part of a 62 slide that I sent to Joanna, is in the middle of a great debate. In the end of the 19th century, we had the debate on can we continue to use Newtonian science? Newtonian science. Can we continue to use Newton science? No the first, no the second. Even though Kant, the philosopher, said it was one of the last followers of Newton. And at the same time, we have the problem of non-Euclidean geometry. We have the newborn statistical mechanics, Gibbs, the concept of entropy. So the problems at the end, we have the birth of a mathematical physical journal. It's not a case that in this period we have this new journal. Not physical, mathematical physical journal, from mathematicists' point of view. So with the rigor of a mathematics, explain that the mathematics is inspired by physical phenomena. I'm not talking about theoretical physicists like I am, for example, that in a heuristic way I study physics without sometimes the rigor of mathematics. Okay? These two things. So in the middle we have this black body radiation theory that had a problem with the specific heat, constant value, etc. And it was in the same times, at the beginning of the century, we have the birth of epistemological current, epistemologists, that study science strictly very good and try to understand from a logical point of view what has happened, until the birth of quantum mechanics, Birkhoff von Neumann, etc. So, to reply to question, in this sense, I don't feel to put the black body radiation in this part of the history of symmetry, because it has a single separated story. Because it's very important, because we are at the beginning of a quanta, and because Einstein gave his idea ad hoc, his hypothesis ad hoc, that harmonic oscillator can be considered not all frequencies, but as one statistical average frequencies. With this, we have the theory of black body radiation that we know nowadays. But if you want to do a history of black body radiation, we have to go back to Kirchhoff, 1854, 55, until Planck. And we see that we arrived to solution because Planck produced three fundamental hypotheses. And one of these was with the help of Einstein, because after that he advanced the relationship between epsilon, energy, and H. For me, it's a separate story.
Thank you. One question here and then the next one there.
Thank you very much for the excellent talk. I just would like to go back for a moment to the point of covariance that you mentioned in your talk, covariance and invariance. And I was wondering if you could elaborate a bit on how you can approach both concepts and their difference from the mathematical point of view and from the physics point of view.
What we can say that nowadays the covariance and invariance from a boat, they represent what I told before, the relation between physics and mathematics. If I have to say that we are talking about physics or we're talking about mathematics, we lose something. If we say that there is a relation, that they represent the end of a study that express a relationship between, and thank you for the question because I would like to say just one thing more. So often this kind of mathematical physical relationships, we talk about the concept of measure. In effect, we measure nothing. We calculate. This is very important because from physical point of view, when we measure, we have statistical approach, error, etc. When we calculate, means that we use the rigor of mathematics. And this is why I say this, the relationship between physics and mathematics. And I don't know if I have time, I can do an example very simple. If we consider the concept of speed as the ratio, distance and time, I can measure distance, and I can do the error with this measure. I can measure the time. I do arithmetically the ratio between space and time, and I have one number that we used to say speed. Okay. We do today with our students this, but during the Renaissance it was forbidden. And after too. Why? Because a man called Euclid said you cannot divide things that are not commensurable. You can divide orange and kiwi. You can divide space and time. This is one of the reasons, because we cannot say in the history of science the real reason, one of the reasons until Galileo, we cannot see this simple equation. The speed is the ratio, is space and time. And Galileo had lots of problems to arrive to do that. This is one of the reasons Galileo did arrive to talk about acceleration like we know nowadays. And this is not the why Newton arrived to do that. But why? And this is the relationship, because Newton said, I'm not interested about space, Euclidean time. In the books, and you are right when you said that is mathematical, Principia Naturalis is a mathematical books. He wrote about a lot about geometry, Apollonius, etc. And what he did? Velocity is a function of two variables, space and time. I do a derivative, I find the derivative of the first order, space on time, and I find the speed. I do a derivative of the second order, space and time, or derivative of the speed and time, I find acceleration. I have no problems with Euclid. Because for Newton, the speed is not a quantity measurable, but a quantity that can be calculated by means of, Newtonian science, by means of function. And because we are talking about a function, that I can do a derivative. Because if speed is considered only a quantity, a number, I can do a derivative of a number. These kind of approaches produce different approach on physics-mathematical relationship in the history of science, and etc. This is why I told before, in this a period after Fourier, 1805, and before Gabriel Lamé, 1865, they wrote together analytical theory, the analytical theory of heat. And Fourier, Gabriel Lamé said, we are not interested in the how can measure if heat, chaleur, caloric, if we have to measure. We are not interested in this. We are interested in equation differential, integral on the volume, and I find the concept of energy. That's all. This is physics, mathematics. They wrote physics, mathematics. They didn't write physical mathematics or mathematical physics. It was just a short period. The same importance of the short period that we used to study electrostatic before to study electromagnetic theory. We study electrostatic and after we abandon. In electromagnetic theory, we find other things. And after we can use the Coulomb law for other things, but it was a case. Electrostatics in the books of physics, it's just it's one chapter. That's all. So this part of the 19th century was before the birth of non-Euclidean geometry, was an important part that permitted to develop, and I stop, permitted to develop some part of certain science in other science. Mathematics in astronomy become mécanique céleste by Laplace. The use of advanced mathematics in mechanics produced in École Polytechnique, one of the first engineering school, a new discipline, structural mechanics we used to do today. And this variation of the paradigm, this anomaly, produce new theories, new discipline, most for teaching and after for research. Thank you.
Last question. We had just time for one more question.
Thank you very much. A really excellent talk. I have something of an anti-question, which is to ask, are you aware of any example where mathematics has disproved the application of a hypothetical symmetry to the physical world? And I'm thinking here of the modern theory of supersymmetry, which is the symmetry between fermions and bosons. And this has been a live theory for 50 years now, and has been the study of intensive experimental searches at the Large Hadron Collider and elsewhere. And you know, at the back of my mind is the fact that although theoretically it is a mathematically possible theory, it might just not be true. So I'd be interested to hear if you can think of an example where there's a symmetry which could in principle be true, but mathematics has shown that it can't be applied in the real world.
Thank you. I try to be fast. Your question is a very epistemic and very interesting. First, I don't think there's something true in the history of science or in the science. Not true, not false. Maybe the theorems can be true or false. Second, I agree with you that we can find something that can disprove with a particular procedure, etc. And to find an example, like you said, you did. But we can find something more if we can take in account, I think starting from Noether until the gauge theory, we can find several situations, not so much, that we, like for example, the four equations of Maxwell, that we can talk about symmetrical, but similarity, no symmetrical, etc. Finally, about the boson 2012, had the privilege to interview a friend of mine that he discovered in Atlas experiment, the boson. And we have to say that until now, from a foundation point of view, we have a boson, we discover a particle with the characteristic of a boson, with a certain field and a very higher energy here by here. But, except error of mine, it is not the Higgs boson like he predicted in 1964. It's not it. So fortunately, for the job and for the physics, we have lots of to do more to arrive to produce experimentally calculations, not measurement, what predicted Higgs in 1964. Still is a theoretical prediction, still is a theoretical prediction with this experimental project near his prediction, but is not the same, exactly the same boson that he proposed, except error of mine.
Thank you. Thank you very, very much. Please, huge applause.